In this lesson, we're going to continue our look at NMR spectroscopy, this time focusing on the interpretation of proton NMR spectra. Proton NMR is possibly the most powerful tool that organic chemists have in determining the structure of organic molecules. The basic principles for proton NMR are similar to those in carbon-13 NMR, except this time it's hydrogen nuclei that are analyzed. The most abundant isotope of hydrogen is H1, or protium. Fortunately, protium has a nuclear spin. In a proton NMR experiment, analyte molecules are placed into a powerful magnetic field, and the hydrogen nuclei align in either the alpha or the beta spin state. Nuclei are then irradiated with radio waves, which flips some of the alpha state protons into the beta state. Those resonances are then plotted to give a proton NMR spectrum. Now, as you're going to see, a proton NMR spectrum is considerably more powerful than a C13 NMR spectrum. A proton NMR spectrum can provide the number of unique hydrogen types in a molecule, it can provide the relative number of each type of hydrogen, it can tell a little bit of information about what types of hydrogen are present, and, most powerfully, it can provide some information on how the various parts of the molecule are connected. So here I have a simple proton NMR spectrum. And you might notice that the frequency range is much smaller than what we saw in a C13 NMR. Here the typical ranges are from about 0 to 10 or 12 ppm. Just like with C13 NMR, I like to break down the frequency range into three separate regions. The lowest region, below about 3 ppm, is the generic alkyl region. Between about 3 and 5 ppm is the electronegative region. Unlike what we saw in C13 NMR, the hydrogens that show up in this region aren't actually bonded to an electronegative atom. If you think about most of the organic molecules we've seen, very few of them actually have a hydrogen bonded to an electronegative atom. The hydrogens in this region are bonded to a carbon that is bonded to an electronegative atom. The rest of the spectrum, above about 5 ppm, is the double bond or pi region. Now, of course, a hydrogen can't be involved in a double bond. So just as we saw with the electronegative region, hydrogens that show up here are on a carbon that is involved in a pi bond. Just as we saw with C13 NMR, a proton NMR spectrum will show a unique resonance for each unique type of hydrogen in the molecule. Nuclei that can be related by symmetry or exchanged via free rotation are chemically equivalent. And chemically equivalent nuclei will share the same chemical shift and show a single resonance. Most organic molecules have a lot more hydrogen atoms than they do carbon atoms, and this can make determining the chemical equivalency of hydrogens a little more difficult. Determining whether two protons are either homotopic, enantiotopic, or diastereotopic to one another can help to determine whether they're chemically equivalent. Homotopic protons are interchangeable by free rotation or by rotation of the entire molecule. Here we see a 3D model of propane. And if you look at the two central hydrogens on that CH2, these hydrogens are homotopic. When we rotate the molecule 180 degrees, one of those hydrogens takes the place of the other, and we can't tell that the molecule has been rotated. Because those two hydrogens are interchangeable by rotating the entire molecule, they're homotopic, and homotopic protons are chemically equivalent. Enantiotopic protons are not interchangeable by rotation, but are reflected by a mirror plane. So here we have a 3D model of 3-pentanol. And you can see as the molecule rotates, you can tell that it has rotated. However, there is a mirror plane that reflects the 3 hydrogens on the far left methyl group to the 3 hydrogens on the far right methyl group. And because those hydrogens are reflected by a mirror plane, they are enantiotopic. And enantiotopic protons are also chemically equivalent. Diastereotopic protons are not interchangeable by rotation or reflected by a mirror plane. Here we have a 3D model of 2-pentanol. If you look at the two hydrogens of the CH2 adjacent to the alcohol, you can see that they are not reflected by a mirror plane, so those are diastereotopic. And diastereotopic hydrogens are not chemically equivalent, and so they will give rise to two separate resonances on a proton NMR spectrum. So here we have a proton NMR spectrum of a very simple molecule. If you look at the structure, you can see that the 3 hydrogens labeled A are all interchangeable by free rotation along that carbon-carbon bond. So those three hydrogens are all chemically equivalent and will give rise to one single resonance. The same thing is true for the three hydrogens labeled B. Those three hydrogens are all interchangeable by free rotation of that carbon-oxygen bond, and therefore they're going to show up as a single resonance. However, since hydrogens A and hydrogen B are not interchangeable by any free rotation nor by a mirror plane, they are not chemically equivalent and will show up as two separate resonances. And if we look at the spectrum, that's exactly what we see. The hydrogens labeled B fall within the electronegative region of the spectrum, and that's because they are attached to a carbon that is attached to an electronegative oxygen. The hydrogens labeled A are in the generic region of the spectrum because they're attached to a carbon that is not bonded to anything electronegative nor involved in a pi bond. One of the reasons that proton NMR is so powerful is because it can provide information about the relative numbers of each type of hydrogen in the molecule. It does this via peak integration, which provides the area under each resonance in a proton NMR spectrum. Integration data can be displayed either numerically or as a step curve. So here I have an NMR spectrum of a simple molecule that includes integration data in the form of a step curve. Starting from the left, you can see that as the curve passes through peak B, it steps up and then levels off until it reaches peak A, where it steps up again and then levels off again. The height of each step as it passes through a peak represents the peak area for that resonance, and the peak area is proportional to the number of protons that peak represents. So on my screen, if I measure the height of the step as the curve passes through peak B, I get 12 millimeters. Measuring the height of the step as the curve passes through peak A, I get 54 millimeters. And 54 divided by 12 is 4.5. So peak A represents 4.5 times as many hydrogens as peak B. Now, of course, you can't have half of a proton. So if we double those values to get everything in whole numbers, we get a 2 to 9 ratio of protons. And if we look at the structure of the molecule, that's exactly what we see. We see 2 identical protons labeled B and 9 identical protons labeled A. And it's worth noting that the protons labeled B are further downfield at higher frequency than the protons labeled A because those protons are on a carbon bound to an electronegative bromine, and so they should show up in that electronegative region above 3. Here we have a proton NMR spectrum of a slightly more complex compound. Here, the integration data is shown numerically above each peak. Looking at the structure, we can see that the 9 hydrogens labeled A are all chemically equivalent by free rotation. These hydrogens are bonded to carbons that are not bonded to anything electronegative nor involved in any pi bonds, so they should show up in the generic region. And if we look at the spectrum, we can see a large peak just above 1 ppm that integrates for 9 protons. The methyl hydrogens labeled B are also generic, but are closer to that carbon-carbon pi bond, pulling them a little bit higher in frequency. And you can see that the peak labeled B integrates for 3 protons. Hydrogen C is attached to a carbon that is involved in a carbon-carbon pi bond, and that means hydrogen C should show up in the pi region of the spectrum, above 5 ppm. And we can see it showing up at about 6.5 ppm, again integrating for 1 proton. Last, we have hydrogen D, which is also attached to a carbon involved in a pi bond, except this time it's a carbon-oxygen pi bond. And that means that this hydrogen will be pulled into the highest part of the pi region. A molecule that has a hydrogen attached to a carbonyl carbon is called an aldehyde, and aldehyde hydrogens typically show up above 9 ppm. And when we look at the spectrum, we see a single resonance up at about 9.5 ppm, again integrating for 1 hydrogen. Perhaps the most powerful aspect of proton NMR is the information that can be obtained because of spin-spin coupling. When a proton is under resonance and is flipping from the alpha spin state to the beta spin state, other nearby protons are doing the same thing. Other nearby protons that are in the alpha spin state will add to the local magnetic field, and nearby protons that are in the beta spin state will subtract from the local magnetic field. This effect is called spin-spin coupling and causes some protons to experience multiple local magnetic fields, which results in peak splitting, creating a multiplet rather than a single peak when a proton is under resonance. Here we have a proton NMR spectrum of bromoethane. If you look at the structure, you can see that it has 2 sets of unique protons, a CH3 labeled A, and a CH2 labeled B. Because the B protons are on a carbon adjacent to that electronegative bromine, they're going to be pulled downfield into a higher frequency and into that electronegative region above 3 ppm. The A protons are generic and show up in the generic region at about 1.5 ppm. Now, you'll immediately realize that the resonances caused by protons A and B look quite a bit different from what we've seen previously. Each resonance is split into multiple peaks, and that splitting is caused by spin-spin coupling with nearby protons. Let's take a look at each set of protons individually. The A protons, shown in green, have two neighboring protons, B, shown in red. Those two neighboring B protons can be either in the alpha spin state or the beta spin state. The magnetic moments caused by those red B protons can either add or subtract to the local magnetic field experienced by the green A protons. Statistically, the two red protons can have their spins either both aligned with the applied magnetic field, both against the applied magnetic field, or one each with and against. That means that the green A protons are actually experiencing three different local magnetic fields. And because the frequency that those protons will resonate at is dependent on the experienced magnetic field, it means that they will show three slightly different resonance frequencies. The higher frequency resonance in that peak occurs when the two neighboring red B hydrogens are both aligned with the applied magnetic field. The lower peak is caused when the two neighboring red B hydrogens are both aligned against the applied magnetic field. The peak in the middle is caused when the two neighboring red B hydrogens have spin states that cancel each other out. And because that's twice as likely to happen as having both of the red B hydrogens in the alpha spin state or both in the beta spin state, the peak in the center is twice as tall. Now let's look at the red B hydrogens and how they are coupled by the neighboring green A hydrogens. The green A hydrogens can also align their spin states either with or against the applied magnetic field. Here, there are actually four possibilities. All three of the nuclei can have their spin states aligned with the applied magnetic field. All three can be aligned against the applied magnetic field. Two can be aligned with the applied magnetic field and one against, or two can be aligned against and one with the applied magnetic field. Because the red B hydrogens experience four slightly different local magnetic fields, they will resonate at four slightly different frequencies, giving rise to four peaks. Because the local magnetic fields that cause the two center peaks are 3 times as likely to occur, those peaks are 3 times higher than the outer peaks. The extent of splitting that a peak experiences due to spin-spin coupling is called its multiplicity. A resonance with a single peak is called a singlet, a resonance with 2 peaks is called a doublet, a resonance with 3 peaks a triplet, and so on. You can see that there's a definite pattern to the relative sizes of the peaks within any given multiplet. Those relative sizes are determined by the statistical probabilities of the different magnetic field environments that cause each one. Those probabilities can easily be determined using a tool called Pascal's triangle. The number of entries in each row of the triangle represents the number of peaks in a given multiplet. So in the first row, we have 1 entry, which represents a singlet. In the second row, we have 2 entries, which represent a doublet, and you can see that the doublet will have a 1-to-1 ratio of peak intensities. In the third row, we have 3 entries, representing a triplet, and you can see that a triplet will have a 1-to-2-to-1 ratio. Now you can see that as we move towards more complex splitting, the outer peaks get comparatively much smaller compared to the innermost peaks. And that means that in higher order multiplets, the outer peaks can actually get lost in the baseline noise of the spectrum. The analysis of spin-spin coupling can be greatly simplified using the n+1 rule. On a proton NMR spectrum, a resonance will be split or coupled into n+1 peaks, where n is the number of a set of identical neighboring protons. Let's go ahead and see how we can apply the n+1 rule to explain the coupling experienced in bromoethane. If we look at the 3 methyl hydrogens here shown in green, they have 2 neighboring red hydrogens. So think of n as standing for neighbor. N here equals 2 neighboring protons. So n+1 would be 3. and that means that those 3 green hydrogens will show up as 3 peaks, or a triplet. And when we look at the spectrum, that's exactly what we see. The 2 red CH2 hydrogens have 3 neighboring CH3 hydrogens. So here, N is 3 neighboring hydrogens, which means that N plus 1 is 4, and 4 peaks is a quartet. So the red CH2 should show up as a quartet. And again, if you look at the spectrum, that's exactly what we see. Learning how to use the N plus 1 rule in reverse is just as important. The peak at about 1.7 ppm is a triplet, and that means that N plus 1 there is 3, and therefore N is 2. So that triplet, the protons that represent that triplet, have 2 neighboring hydrogens. And because this peak integrates for 3, I now know that I have 3 identical protons, most likely a methyl group, with 2 neighboring hydrogens. The resonance at about 3.3 is a quartet, and that means that N plus 1 is 4, so N is 3. And because this peak integrates for 2 hydrogens, that means that we have a CH2 adjacent to 3 identical protons, most likely a methyl group. So you can see that the power of spin-spin coupling is that it allows you to figure out which sets of hydrogens are next to which in the molecule. The distance between any 2 adjacent peaks in a multiplet is called the coupling constant, and it's reported in Hertz. A useful feature of coupling constants is that when 2 hydrogen types are coupling one another, they will share the exact same coupling constant. So here I have the triplet and the quartet from bromoethane, and you can see that the spacing between any 2 adjacent peaks in either resonance is a constant. And because the coupling constant in each of those multiplets is the same, it means that those 2 hydrogen types are coupling to one another. In other words, you know that those 2 hydrogens are next door to each other. Comparing coupling constants can actually be really useful in more complicated spectra where you have lots of multiplets. It can enable you to figure out which peaks are coupling to one another and which aren't. So let's take a look at a few more proton NMR spectra. There's a lot of information to pull out of any spectrum. Counting the number of peaks will tell you how many unique types of hydrogen are in the molecule. The chemical shift of each peak can tell you a little bit about what kind of hydrogens they are. The integral value can tell you how many of those hydrogens there are, at least in a relative sense. And the splitting pattern, or multiplicity, can tell you how many neighboring protons each set has. Looking at this spectrum, we can see 3 resonances, so we know we have 3 unique types of hydrogen. One resonance is in the electronegative region, which means that those hydrogens are on a carbon bonded to an electronegative atom. The integral value for that peak tells us that there is 1 proton for that resonance. And seeing that this resonance is a septet tells us that it has 6 identical neighboring hydrogens. And the easiest way to have 6 identical hydrogens is by having 2 methyl groups. When we look at the structure, we can see that hydrogen C is on a carbon bonded to an electronegative oxygen, so it's going to be pulled downfield into high frequency. And that carbon that holds hydrogen C, there are 6 neighboring identical hydrogens, represented by those 2 identical methyl groups, and they're identical because of the mirror plane. So with 6 identical neighboring hydrogens, N is 6, N plus 1 is 7, and so we see a septet. On the spectrum, we also see a very large doublet just above 1 ppm. So it's in the generic region, and it integrates for 6 hydrogens. And again, the easiest way to have 6 identical hydrogens is to have 2 identical methyl groups related by, say, a mirror plane. That resonance is a doublet, and that means that those 6 hydrogens must be next door to 1 hydrogen, N plus 1 is 2. And when we look at the structure, we can see that we have 6 identical CH3 protons labeled A, and all of those A protons are right next door to a carbon with proton C, and there's only 1 of those protons, so with 1 neighbor, N is 1, N plus 1 is 2, and that's why those 6 hydrogens show up as a doublet. The only hydrogen left on the structure is the hydrogen of the alcohol, the OH hydrogen. And hydrogens that are bonded directly to an oxygen or a nitrogen actually behave rather strangely in a proton NMR. They can show up almost anywhere in the spectrum, but typically between 2 and 5 ppm is where you'll see them. Protons bonded directly to an oxygen or a nitrogen often don't participate in spin-spin coupling, so you'll often see them as singlets. Now, looking at the resonance for that B hydrogen, you can see that it actually has sort of a broadened out bell shape. It's actually caused by hydrogen bonding. and it can make spotting hydrogens that are bonded directly to nitrogen or oxygen a little bit easier. Looking at the next spectrum, we can see that there are only two resonances. One of them occurs in the electronegative region at about 3.4 ppm, and the other in the generic region just below 2. The higher frequency resonance integrates for 4 hydrogens, and typically that means you have 2 identical CH2s. We can also see that this peak is a triplet, so that means that n plus 1 is 3, so n is 2, and these 4 hydrogens must therefore have 2 neighboring hydrogens. And when we look at the other peak in this spectrum, we can see that it integrates for 2. We can also see that it has a multiplicity of a quintet, and that means that it must have 4 identical neighboring hydrogens. Looking at the structure, we can see that there are 2 A hydrogens, and those A hydrogens are flanked by 2 identical CH2s. So the A hydrogens have 4 identical neighbors, so n equals 4, n plus 1 is 5, and that's why they're split into a quintet. The B hydrogens are pulled downfield because of their proximity to that electronegative chlorine. We can see that they are related by a mirror plane, and that each set of B protons has 2 neighboring A protons. So n is 2, n plus 1 is 3, and that's why the B protons show up as a triplet. Now, this next spectrum is definitely going to ratchet up the difficulty level. If we look, we can see 6 unique resonances on this spectrum, and all but one of them show up in the pi region. Peak A actually shows up in the electronegative region, and it integrates for 3 protons, and it's a singlet. And if we look at the structure, we can see that A is actually a methoxy group attached to that benzene. Those hydrogens are on a carbon bonded to an oxygen, which would pull those hydrogens into the electronegative region, and those hydrogens have no neighboring hydrogens. There's an oxygen next door with no hydrogens attached. So here, n is 0, so n plus 1 is 1, and that's why it's a singlet. Looking at the structure, we can see that aldehyde hydrogen labeled F. We know that that aldehyde hydrogen is attached to a carbon that is involved in a pi bond, so it's going to be in the pi region, and because it's on a carbonyl carbon, it's going to be at the extreme high end of that range. So we can see hydrogen F showing up at about 9.5 ppm, and it's showing up as a doublet. When we look at the structure, we can see that hydrogen F is next door to a carbon with 1 hydrogen, hydrogen B. So n is 1, n plus 1 is 2, and that's why F is a doublet. Hydrogen E is similar. Hydrogen E is on a carbon that is involved in a pi bond. However, this time it's an alkene, so it's going to be in the lower end of the pi region. And looking at the structure, we can see that hydrogen E is on a carbon that has 1 neighboring hydrogen, hydrogen B. So hydrogen E should also be a doublet. Now, it may be hard to see, but there's actually a mirror plane in this molecule. The mirror plane goes diagonally straight through the benzene ring, and it reflects those 2 C hydrogens to one another and those 2 D hydrogens to one another. However, there is no mirror plane that can reflect the C hydrogens to the D hydrogens. We can see that there are 2 C hydrogens, and each one has 1 neighboring D hydrogen. So n equals 1, n plus 1 is 2, and that's why C shows up as a 2 hydrogen doublet. The D hydrogens are pretty much the exact same thing. There are 2 of them. Each one has 1 neighboring C hydrogen, so n is 1, n plus 1 is 2, so the D hydrogens will show up as a doublet and integrate for 2. The only hydrogen left to look at is hydrogen B. There's only 1 hydrogen B, and it's bonded to a carbon that's involved in a double bond to another carbon. So it should show up in the pi region and in the lower end of the pi region. Hydrogen B has 2 neighbors, an E hydrogen to the left and an F hydrogen to the right. And so you may be tempted to say, oh, 2 neighbors, n is 2, n plus 1 is 3, so B should show up as a triplet. But when you look at the spectrum, B is definitely not a triplet. And that's because we misapplied the n plus 1 rule. When we apply the n plus 1 rule, and we look for neighboring hydrogens, we have to apply the n plus 1 rule once for each unique type of neighboring hydrogen. What's different here is that hydrogen B actually has 2 totally different kinds of neighbors. E and F are not the same kind of proton. And because they're not the same, they can't be lumped together into one n for the n plus 1 rule. What we need to do is apply the n plus 1 rule once for each of those 2 unique neighbors. So there's 1 E hydrogen next door, so n is 1 and n plus 1 is 2. So E will split B into a doublet. Now B also has a neighboring F hydrogen, and there's 1 of those. So n is 1, n plus 1 is 2, So F will split B into a doublet. And when you take something and split it into half twice, you get 4. And that's why we see this strange splitting pattern for B. You can see that B actually has 4 peaks. But it's important to recognize that it's not a quartet. A quartet would have been caused by having 3 identical neighboring hydrogens. The coupling constant between any 2 adjacent peaks in that quartet would also be consistent. And as we saw before, a quartet will have a 1 to 3 to 3 to 1 ratio of peak intensities. What we see for the B hydrogen resonance is called a doublet of doublets. Again, we're taking the original singlet resonance, splitting it in half by the coupling to E, and then splitting that in half again by the coupling from F. And because the relative peak intensities in a doublet are 1 to 1, and we've essentially split this twice into a doublet, that's why we see a 1 to 1 to 1 to 1 ratio for those 4 peaks. You can also see that the 4 peaks aren't evenly spaced, and that's because there are 2 couplings going on, and that means that B is actually experiencing 2 different coupling constants. One coupling between B and E, and a slightly different coupling between B and F, and those will have different coupling constants. Our last spectrum is a bit of a sneaky one. It's a very simple looking molecule. If you look at the structure, you might be tempted to say there are only 2 hydrogen types on this molecule, but there are in fact 3. It should be clear that hydrogen C is unique. It's attached to a carbon that's involved in a double bond, so it should be in the pi region, and that carbon is also attached to an electronegative chlorine, which will push it further downfield than the other 2 hydrogens, which are also attached to a carbon involved in a double bond. What's probably surprising is that hydrogens A and B are not chemically equivalent. They're actually different. Technically, they are diastereotopic to one another. Hydrogens A and B cannot be reflected to one another with a mirror plane, and they cannot be interchanged by free rotation because they're attached to a carbon that's involved in a double bond, and double bonds cannot undergo free rotation. One way to look at it is to simply say that hydrogen B is trans to hydrogen C, and hydrogen A is cis to hydrogen C. And because hydrogens A and B cannot be interconverted, they must be different. Now, they are, of course, very similar. In fact, if you look at the spectrum, you can see that the computer actually lumped the 2 together when it integrated them. When we look at the multiplicities, take a look at hydrogen C. Hydrogen C has 2 neighbors, but those neighbors are not the same as one another, which means we have to apply the n+1 rule twice, once for each unique neighbor. And that means that hydrogen B will couple C into a doublet, and hydrogen A will couple C into a doublet. And that means C will be a doublet of doublets, an unevenly spaced set of 4 equally intense peaks. And that's exactly what we see on the spectrum. Hydrogens A and B are so similar that they're stacked on top of one another, and it's really impossible to see what's going on there. Regardless, if we analyze the couplings, you'll see that hydrogen B has 2 neighbors, hydrogen C on the next carbon, and because hydrogen A is actually different, it's going to couple hydrogen B as well. This is actually called geminal coupling, when hydrogens on the same carbon couple one another. Normally, hydrogens on the same carbon end up being chemically equivalent, but when there's a limitation on free rotation because of a double bond or because of a ring, they can actually end up being unique from one another. And unique hydrogens that are close by will couple to one another. So hydrogen B will be split into a doublet by C and into a doublet again by A. And hydrogen A will be split into a doublet by hydrogen C and split again into a doublet by hydrogen B. And that means that what you're going to see here is 2 doublets of doublets, a doublet of doublet for B and a doublet of doublets for A. 8 peaks all smashed on top of each other just below 5.5 ppm. Now, that portion of the spectrum is not really very interpretable, but it is really instructive. We're going to wrap up our look at proton NMR with a simple table of useful chemical shifts. Just like what we saw with C13 NMR, we can break down the spectrum into 3 regions. I actually like to break down the pi region into 3 separate subregions. Hydrogens that are actually attached to an alkene typically show up between 4.5 and 6.5 ppm. Alkene hydrogens. Hydrogens that are attached to a benzene ring show up a little higher, typically between about 6.5 and 8.5 ppm. On a C13 spectrum, you really couldn't tell the difference between an alkene carbon and a benzene carbon. But on a proton NMR, you can actually tell the difference between a hydrogen on an alkene and a hydrogen on a benzene ring. If you've never seen the abbreviation pH, that actually stands for phenyl, which is C6H5. And C6H5 bonded to hydrogen is just benzene. At the extreme high end of the pi region, we have hydrogens attached to a carbonyl, and again, that's called an aldehyde, and they typically show up around 9 or 10 ppm. In the electronegative region, we have hydrogens that are attached to carbons that are bonded to something electronegative, like an oxygen or a halogen. The hydrogens attached to the sp carbon of a terminal alkyne also show up in the low end of this region. And then last, we have the generic region, and this is where hydrogens attached to carbons that aren't bonded to anything electronegative and aren't involved in pi bonds are going to show up. At the very low end of this range, we have hydrogens that are attached to a carbon that's bonded to silicon. And just like what we saw with C13NMR, the hydrogens of tetramethylsilane are used as the standard to define 0.